This is SpaceTime Series 21, Episode 6. Coming up on SpaceTime. How big can a neutron star get? New clues about the recipe for making stars. And forget what you've heard, there is no link between big earthquakes and the full moon. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims super-dense stellar corpses known as neutron stars probably couldn't get much bigger than about twice the mass of our Sun. The findings, reported in the Astrophysical Journal, help solve a 40-year-old mystery which has been baffling scientists ever since neutron stars were first discovered. Neutron stars are the stellar corpses of stars far more massive than the Sun. A star shines because its immense mass generates so much extreme temperature and pressure at its centre that it crushes hydrogen atoms together, fusing them to form helium atoms. Astronomers refer to stars doing this as being on the main sequence. Eventually, when the hydrogen in the star's core runs out, it begins fusing helium into oxygen and carbon, in the process getting cooler, growing bigger and more bloated. This is a star's red giant phase. For the majority of stars, such as our Sun, once the helium in the stellar core is exhausted, the star's bloated outer envelope floats away as a planetary nebula, leaving behind a white-hot oxygen-carbon core about the size of the Earth, known as a white dwarf, which will slowly cool over the eons of time. However, stars, say more than 8 times the mass of our Sun, are destined to experience a very different fate. That's because they're so massive that once they've fused their core helium into oxygen and carbon, they can then fuse this oxygen and carbon into progressively heavier atoms, eventually forming an iron core. However, no matter how massive a star is, it can't fuse iron into even heavier elements. Instead, these massive stars undergo what's known as a core collapse supernova event, an explosion so powerful it can literally outshine an entire galaxy. This blasts most of the progenitor star apart, in the process producing most of the other elements on the periodic table. Left behind is a super-dense object only a dozen or so kilometres wide, known as a neutron star. Neutron stars are so dense, hot and under so much pressure that their positively charged protons and negatively charged electrons are literally crushed together to form neutrons, hence the star's name. Scientists had previously worked out that neutron stars can have as little as 1.4 times the mass of the Sun, a figure known as the Chandrasekhar limit, and the point where temperatures and pressures are sufficient to overcome electron degeneracy, allowing the dying star to collapse beyond the white dwarf phase. But up until now, no one's been able to determine the upper limit. Just how massive can a neutron star be before it has to collapse in on itself to form a black hole? Scientists always figured it was somewhere around 3 solar masses before neutron degeneracy pressure would be overcome and a black hole created. While most neutron stars have a mass of around 1.4 times that of the Sun, some neutron stars have been found with more than twice the Sun's mass. The density of these stars is enormous. It's as if the entire Himalayan mountain range were compressed into a beer mug. And the indications are that a neutron star at maximum mass would collapse to form a black hole if even just a single additional neutron were added. But exactly what that mass would be remains a mystery. Now, scientists from the Frankfurt Institute of Advanced Studies and the Goethe Institute in Germany have successfully calculated a strict upper limit for the maximum mass of neutron stars. With an accuracy down to just a few %, the maximum mass of a non-rotating neutron star cannot exceed 2.16%. The findings were achieved using a process called universal relations, which implies that practically all neutron stars look alike, meaning that their properties can be expressed in terms of dimensionless quantities. The study's authors combined these universal relations with observations from last year's first ever confirmed detection of the merging of 2 neutron stars. As the stars merged, they converted some of their energy into gravitational waves, which were then picked up by the LIGO-Virgo collaboration. The merger also emitted energy across the electromagnetic spectrum, allowing astronomers to see a gravitational event for the first time. And these observations simplified the calculations tremendously by making them independent of the equation of state. This equation is a theoretical model for describing dense matter inside a star that provides information on its composition at various steps within the star. The universal relation played a key role in defining the new maximum mass. The authors say they'll use future gravitational wave observations of neutron star mergers to further refine their findings. You're listening to Space Time. I'm Stuart Gary. Astronomers have shed fresh light on the importance of hydrogen atoms for the birth of new stars. Only cool hydrogen molecules are thought to directly fuel star formation. But the new research reported in the astrophysical journal Letters has shown that there's more hydrogen atoms than molecules, even in young galaxies which are making lots of new stars. The study's lead author, Dr. Luca Cortez from the University of Western Australia, says new stars are constantly forming in dense clouds of molecular gas and dust found in galaxies. In fact, our own galaxy, the Milky Way, forms roughly one solar mass worth of new stars every Earth year. In the local universe close to us, about 70% of the hydrogen gas is found as individual atoms, with the remaining 30% in the form of molecular hydrogen. Astronomers had expected that as they look further back through space-time, younger and younger galaxies would contain more and more molecular hydrogen until it became the dominant form of hydrogen in a galaxy. But much to their surprise, they've instead found that atomic hydrogen also makes up the majority of gas in younger galaxies. And this is true even for galaxies under conditions similar to what we call the cosmic noon. That's a period about 7 billion years after the Big Bang, when the rate of star formation in the universe had reached its peak. Cortez says astronomers did discover young star-forming galaxies at cosmic noon with 10 times more hydrogen molecules than the Milky Way. And with such large reservoirs of molecular hydrogen, it's thought no room would be left for comparable amounts of cold atomic hydrogen gas. Unfortunately, it's currently impossible to detect hydrogen atoms at such large distances in order to verify this expectation. So instead, Cortez and colleagues discovered a population of galaxies some 3 billion years younger than the Milky Way, hosting gas reservoirs at least as large as those of galaxies at cosmic noon. But much to their surprise, they found that despite hosting 10 billion solar masses worth of molecular hydrogen in these young galaxies, it turns out they're also extremely rich in atomic hydrogen as well. In other words, the balance between atomic hydrogen and molecular hydrogen was pretty much the same back then as what it is in the Milky Way now, with atomic hydrogen still dominating. The authors made their discovery using data from two of the world's most powerful radio telescopes, the 305-metre Arecibo Observatory in Puerto Rico and ALMA, the European Southern Observatory's Atacama Large Millimetre Submillimetre Array telescope in Chile. Cortez says these new findings have tremendous implications for science's understanding of the early universe.
Our current view of star formation suggests that stars are formed out of hydrogen gas, and great part of the hydrogen gas in the local universe is observed in the form of simple atoms. This is low-density, relatively low-temperature gas that rotates in the disk of galaxies. Now, this atomic gas in itself is not able to collapse and form stars. We need to change phase because the gas needs to become denser and then to be able to collapse and form stars. And this happens via the condensation of atoms into molecules, and so this is why molecular hydrogen is a critical step to form stars. So understanding both the atomic and molecular phases give us a complete picture of the, let's say, what we call is the reservoir for star formation in galaxies.
Would you expect to find lots of these clouds, therefore, in the early history of the universe when star formation was, say, more prevalent than what it is today?
Correct. That was the original expectation. So, as I mentioned, in our own Milky Way, the molecular clouds form only roughly 1/3 of the total reservoir of hydrogen in galaxies that support star formation. And the idea was that, as you said, now in the local universe, the star formation activity of galaxies is factor of 10 lower than it was, let's say, when the universe was half of its current age. When we look at galaxies when the universe was just, let's say, 6 or 7 billion of years old, we find that galaxies as big as the Milky Way were forming stars at significantly higher rate, a factor of 10 or a factor of 100. So the expectation is that these galaxies contain much more molecular hydrogen than we see in the local universe.
Is it easy to look for molecular hydrogen or even atomic hydrogen that far back in space-time?
Well, there are pros and cons in both approaches. So atomic hydrogen, we can, let's say, look at it directly because atoms emit directly photons due to a transition that happens in the energy state of the the atom, or the hydrogen atom itself.
Yeah.
Yes. Instead, an hydrogen molecule doesn't have what we call a dipole, so it's not able to emit directly a photon. So we are completely blind to be able to directly measure the amount of molecular hydrogen in galaxies. What we use is what we call a proxy, because we think that in molecular clouds, hydrogen is very tightly bound to another molecule, which is the carbon monoxide, which instead emits very brightly in the millimeter range. And so what we generally do in astronomy is we measure how much carbon monoxide there is in galaxies, and we try to convert it into a mass of molecular hydrogen.
When you look for galaxies which, say, could represent something that would exist in 6 billion years after the Big Bang, 7 billion years after the Big Bang, you got a surprise.
Oh yes, absolutely. I mean, this is easy on paper. Then the problem is that we don't really understand the physics of the relation between carbon monoxide and molecular hydrogen. Of course, we can test it in the local universe, but when we go at very, very early ages of the universe, the physics becomes very different. And this is something interesting that we are seeing, is that, as I was mentioning, we were expecting to find a reversal in the balance between atomic hydrogen and molecular hydrogen in the, in the earlier universe, with molecules being more abundant. Instead, now what we are seeing is that actually the balance between the two phases remains pretty much constant, which is kind of interesting.
That must have been a bit of a surprise, because the star formation rates would have been very different.
Yes, it's a surprise because astronomy has evolved significantly quicker in the ability of detecting carbon monoxide at earlier ages than not as it has evolved in detecting, atomic hydrogen at earlier ages. So in the last few years, we've detected a lot of molecular hydrogen. So in absolute values, absolutely, the early galaxies have a lot of molecular hydrogen. In general, 10 times more than in our own Milky Way. What we discover now that we're able to push radio telescope to similar distances is that we also find similarly large reservoir of atomic hydrogen. So everything is scales up, but the relative relation between atoms and molecules seems to remain the same.
Was that a surprise?
It was something that at the moment the community was kind of divided into two. Mm-hmm. There were part of the community was kind of thinking there can be atomic hydrogen there because we have so much molecules that we don't really need additional atomic hydrogen. While the other part of the community was thinking, it's not really clear, we don't know, why can't exist such a huge reservoir? And so what we tried very hard is to push current instrumentation to the limit and to show that actually at the moment we don't have a variation in the phase transition between atoms and molecules at higher redshift. It depends who you talk to whether it was a surprise or not. It's definitely very interesting because we are setting a significant constraint in our modeling for how stars form also in the earlier universe.
That's Dr. Luca Cortez from the University of Western Australia node of the International Centre for Radio Astronomy Research. I'm Stuart Gary. You're listening to SpaceTime. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. The good citizenry of the American Midwest have been treated to an unexpected celestial spectacular, with their evening skies lit up by a bright meteor and sonic boom. People in the states of Ohio and Michigan and across the border in Ontario, Canada, witnessed the event at around 8 o'clock local time. The American Meteor Society received hundreds of reports of the fireball. The National Weather Service, America's Weather Bureau, were able to confirm that the flash and boom were not associated with thunder or lightning or any other meteorological event. They say the most likely cause was a meteor, estimated to be about 182 centimetres wide, travelling at about 45,000 kilometres per hour before breaking up as it hit thicker atmosphere at an altitude of about 32 kilometres. The US Geological Survey says the event registered a magnitude 2 on the open-ended Richter scale and shook houses across much of eastern Michigan as it airburst about 7 kilometres east of St. Clair Shores. This is Space Time. I'm Stuart Gary. A new study has provided more evidence to dispel the enduring myth that large earthquakes tend to happen during certain phases of the moon or at certain times of the year. The findings reported in the journal Seismological Research Letters confirms that this bit of earthquake lore, that's lore spelled L-O-R-E, is incorrect. The idea that the sun and the moon's positions in the sky can modulate earthquake rates has a long history. Charles Richter, who developed the Richter scale to measure the strength of seismological events, was bombarded by heaps of letters from amateur predictors, all suggesting a link between earthquake events and the gravitational tidal pull of the moon and sun on the Earth. Scientists reached their conclusions after matching dates and lunar phases to 204 earthquakes of magnitude 8 or greater. The study's lead author, Susan Hugh from the US Geological Survey, found there was no evidence that the rates of these giant earthquakes is in any way affected by the position of the Earth relative to the moon or sun. She says the patterns that some observers see linking large earthquakes with specific parts of the lunar cycle are no different than the types of patterns which would come up from completely random data. To reach their conclusions, scientists examined the date of 204 large earthquakes from a global earthquake catalogue and compared each earthquake to the lunar phase at the time. To ensure a fair coverage, they went all the way back to the 1600s. And to avoid detecting clusters of earthquakes that are all related to one another from the same event, the authors chose to look at only larger earthquakes because they're less likely to be aftershocks from a single bigger event. Looking at only larger earthquakes also allowed the authors to pare down the list to manageable numbers, which could then be matched to lunar phase information found in databases. The analysis did turn up some clusters of earthquakes on certain days, but to test for any significance in the patterns being observed, researchers randomised the dates of the earthquakes in order to find out if any patterns would appear in the random data. They found that the patterns in the random data were no different from the kinds of patterns showing up in the original data set. Hugh says that's not an unusual finding. After all, when you flip a coin, you can sometimes end up with 5 heads in a row. But over a larger set of flips, it will all even out. Now, Hugh admits she did see some unusual signals in the original data. For instance, the highest number of earthquakes, 16 occurring on a single day, came exactly 7 days after the new moon. That's when the moon's on the same side of the Earth as the sun. But the signal's not statistically significant, and the lunar tides would have been at minimum at this point anyway, so it doesn't really make any physical sense. Now, no one's denying that the sun and the moon do cause solid Earth tidal stresses, ripples through the Earth itself, in addition to the waters hitting the coastline. And it could be one of these stresses which are contributing in a very small way to earthquake nucleation. Some previous studies have shown that there is, in some cases, a weak effect where there are more earthquakes when tidal stresses are high. But the authors of those papers are all careful not to claim that their data could be used for prediction purposes, because the modulation's always very small. Hugh says sooner or later there's going to be another big earthquake on a full moon, and of course the lore, that's spelled L-O-R-E, will pop up again, with the obligatory I told you so. However, she says the new study at least provides a solid scientific foundation to show that over the long term, there isn't a good track record of big earthquakes happening on full moons. I'm Stuart Gary. You're listening to Space Time. A new study has confirmed that just like Earth, Saturn's moon Titan has a sea level. It seems just as the surface of oceans on Earth lie at an average elevation, which we call sea level, Titan's seas also lie at an average elevation. The discovery, reported in the journal Geophysical Research Letters, adds to a growing list of similarities between Earth and this alien hostile world. The 5,150 kilometre wide Saturnian moon is about 50% larger than the Earth's moon, and about 80% more massive. It's also the only world we know of other than Earth to have rain, which falls to form running streams and rivers that eventually flow into lakes and oceans. However, with an average surface temperature around minus 180 degrees Celsius, the liquids on Titan aren't water, which is frozen solid, forming much of the moon's bedrock. Instead, they're liquid methane and ethane hydrocarbons. The study's lead author, Alex Hayes from Cornell University in New York, says Titan's seas follow a constant elevation relative to Titan's gravitational pull, just like Earth's oceans. It turns out smaller lakes on Titan appear at elevations several hundred metres higher than Titan's mean sea level. And lakes at higher elevations are also commonly found here on Earth. In fact, the highest lake navigable by large ships, South America's Lake Titicaca, is at an elevation of over 12,000 feet or 3,700 metres above sea level. The new findings imply that Titan's major liquid bodies are connected under the surface in something akin to an aquifer system on Earth. Hydrocarbons appear to be flowing underneath Titan's surface, similar to the way water flows through underground porous rock or gravel on Earth, so that nearby Titanian lakes are communicating with each other and sharing a common liquid level. The findings are based on data collected by NASA's Cassini radar instrument. Cassini arrived at Saturn in 2004, undertaking a 13-year mission of exploration studying the ringed world and its many moons. The probe finally ended its historic mission in September with a suicidal death plunge into the planet's crushing atmosphere. I'm Stuart Gary, you're listening to SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Analysis by the World Meteorological Organization of 5 leading international datasets has confirmed that 2017 is the third warmest year on record. Scientists found increasing atmospheric concentrations of greenhouse gases was the cause for the continuing trend of warmest years, with 2017 joining 2015 and 2016 in the record books. While the global record still held by 2016, 2017 was the warmest year without an El Niño, which can boost global annual temperatures. Of course, the World Meteorological Organization's global findings haven't come as a surprise, with the Australian Bureau of Meteorology also listing 2017 as Australia's third hottest year on record. The Earth is now about 1 degree Celsius warmer than what it would be without the impact of human activities, especially greenhouse gas emissions from the burning of fossil fuels. In fact, the amount of carbon dioxide in Earth's atmosphere has now officially passed 410 parts per million, a record high in human history and the highest it's been in millions of years. The milestone was recorded at the Mauna Loa Observatory in Hawaii by the University of California, San Diego. The planet reached the psychological milestone of 400 parts per million just a few years ago. Making matters even worse, the new record high was reached months before the expected annual peak for CO2 emissions. Bit of good news now. Scientists have developed a new blood test capable of detecting 8 of the most common cancers, many of which are often only diagnosed when it's too late. The new blood test can screen for ovarian, liver, pancreatic, esophageal, bowel, lung and breast cancers. Until now, many of these cancers were already well advanced by the time they were picked up. The test, reported in the journal Science, is designed mainly for people over the age of 50 and could be available within 2 years. A team of Australian and US researchers trialled the blood tests on more than 1,000 cancer patients. The test is sensitive to mutated DNA floating freely in the blood and cancer-related proteins. It was able to detect tumours in 70% of patients on average. The war in Syria has entered a new phase, with Russia claiming its troops are now coming under attack from armed drones. Moscow says 10 drones equipped with explosives attacked Russian air bases in Syria, while 3 others targeted a Russian naval base there. The Russian Defense Ministry says while there were no casualties or damage in these incidents, the same technology could be used to carry out terrorist attacks. The drones that attacked the bases were each fitted with 10 explosive devices, each device weighing 400 grams. The devices were filled with ball bearings designed to act as shrapnel to cause maximum injury. The Russian military have now spent over 2 years in Syria supporting the dictatorship of Bashar al-Assad's regime. A new study has found that crops such as hops and rye would grow well in Martian soil with just a little fertiliser. Researchers from Villanova University in Pennsylvania used an accurate replication of Martian soil to see which crops would grow on the red planet. 45 kilograms of Martian soil was made using crushed basalt from an extinct volcano in California's Mojave Desert. Scientists grew 14 types of plants, including hops, rye, kale, potatoes, mint, basil and carrots. The plants were grown in either simulated Martian soil, simulated lunar soil, or regular Earth soil as a control. Scientists say Martian soil is dense and dries out quickly. But almost all the plants thrived when scientists added a bit of vermiculite, a mineral often mixed in with heavy and sticky earth soils. Now here's something I bet you're not asked every day. Have you ever sneezed hard enough to punch a hole in the back of your throat? Well, apparently it's actually happened to a man in the UK. A study published in the British medical journal Case Reports says the patient tried to hold in his sneeze by pinching his nose and clamping his mouth shut. However, the force of the sneeze literally ruptured the soft tissue in the back of his throat, leaving him barely able to speak or swallow and in considerable pain. The patient also reported hearing popping and cracking sounds as air passed through the newly created hole. While this condition is extremely rare, the doctors who treated the patient warn against holding your nose and mouth to avoid a powerful sneeze. The world's largest consumer electronics show, CES, is wrapped up for another year in Las Vegas. And this year's show was notable not just for its flood of new technology, but also for the heavy rains which caused a flood of a very different kind. All that water led to power blackouts, shining an unexpected light on the show. Alex Zaharov-Reutt from IT Wire was in the midst of it all, and he joins us now.
It was 10 days of technological heaven. It was the biggest CES thus far in history. It had multiple venues, and there were even several side events going on. And there's lots of talk about robots in various articles at CES. On a scale of caveman to Isaac Asimov, a lot of these robots are just like the black and white era of technology. You know, they're like little companions. They can operate as Bluetooth speakers on wheels and even answer sort of simple questions, but they're not the kind of robots you would expect from Asimov's iRobot series or anything like the kind of androids that you would expect that our science fiction writers have dreamt up. But I did see a lot of artificial intelligence from Google Assistant. Google was everywhere with their advertising. Amazon Alexa, and also lots of HomeKit, Siri, Apple-enabled devices that were sort of all over the show floor with a lot of TVs and robot kitchen equipment and all manner of devices able to primarily be controlled by voice. The digital assistant capability was everywhere, and you will, over the course of this year, if you go into retail stores, you will see more and more devices that you can control via voice and via your phone, which is pretty amazing.
Last week you told us about the wall. Having had the whole experience now of CES, what's the big thing? What's the thing that is going to affect you, me, and everybody else listening to this program right now?
Well, it's what I was just saying, artificial intelligence, being able to communicate with your devices by voice, bringing forth that Star Trek-like future where you speak to your computer. It's a natural part of the interface and you don't have to think twice about it. Obviously, there's still refinements to go. I saw flexible touch-enabled screens that could be molded to any surface. You could have curved displays in your car. Instead of having a dashboard with buttons, it's just sort of curved like this futuristic lounge chair. And next to you is this huge pad. And I've got videos, actually, if people have a look at youtube.com/AlexOnTech. I've got about 20 different videos of these interviews that I did with all these things I'm about to tell you that you can see for yourself. I thought this car with just a fully touch-enabled display was just a mock-up, but he was touching the buttons. It was real.
Now, is this the car without the steering wheel?
No, this had a steering wheel. So, look, there were, all the major car companies were there. Look, I saw anti-ransomware backup software. I saw a personal computerized laser engraving system. You can stick it on your desk. It's this big thing. You can stick anything inside and laser engrave anything you want onto it. I saw plant growing systems. I saw wireless chargers. There was a gadget that went onto the back of a bike that could automatically detect cars that were speeding, all of the cars that had been in a certain spot for longer than they were meant to be there for, and other infringements. And all this information could be sent back to the local area command for the police to then go out and investigate. I saw a computer system for kids that was like digital Lego. You could program it. You could add things to it. At one of the big TV stands that had laser TVs. And this was from the Hisense stand. They actually had this dancer. She was sort of playing these beams of light like it was an instrument. There were 3D TVs at very high resolution that required no glasses. So the glasses-free 3D TV has arrived.
That's going to be huge. That'll be a big one.
Yeah, well, the glasses were always a pain. There was a credit card. It has a little e-ink screen the size of a square QR code. And in that little screen, any sort of message can be programmed, from your credit card details to a picture of yourself to a QR codes. But it's also got a SIM card inside. It picks up the electricity from the air, from radio waves, and sort of charges the battery inside. And it allows you to have a whole stack of different credit cards or debit cards or shopping cards inside. If one of the cards gets somehow compromised, the bank can just delete that card and send a new card to that card over the air. It was ultra-modern version of the credit card that you have now. And it's coming to Australia this year. It's coming to a whole stack of banks.
That's Alex Zaharov-Reutt from IT Wire. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.